Welcome to this NPTEL lectures on robotics, basics and advanced concepts. In this week, we'll look at kinematics of serial robots. Contents of this week are basically we'll introduce the concepts in kinematics, some important concept in kinematics. Then in the rest of the lecture, I will look at direct kinematics of serial robots. In the next lecture, we'll look at inverse kinematics of serial robots. In lecture 3, we'll look at inverse kinematics of serial robots in two special cases. So when the number of links is less than 6 and when the number of links is greater than 6. And finally, in the last lecture in this week, we will look at elimination theory and solution of nonlinear equations. So basically, we'll see that we always have to solve nonlinear equations, and I will present a method called elimination theory, which can be used to obtain solutions to these nonlinear equations. And we'll use this elimination theory to show you how the inverse kinematics of a general 6 degree of freedom 6R robot can be solved. So let's continue. So introduction. A serial manipulator is basically one where one end is fixed and then you have bunch of links and joints, and then it ends up with a free end, which is often called as the end effector. Okay. So in kinematics, basically we look at motion of rigid links without considering forces and torques. So what do we study? In kinematics, we study the geometry of the motion. Okay, we'll see what geometry of the motion really means. In these lectures, we will assume that the serial manipulator has been modeled using Denavit-Hartenberg parameters. In the last week, I showed you that the links of a robot can be modeled using 4 Denavit-Hartenberg parameters, namely the twist angle, the link length, the joint rotation, and the link offset. Okay, so we are going to use the Denavit-Hartenberg convention, which we discussed and presented last week. There are two main problems in kinematics. One is called as the direct kinematics problem, and the other one is called the inverse kinematics problem. So let's quickly look at a few examples of serial robots. We have seen some of these earlier. On the left, we have a planar 3 degree of freedom robot. This is the simplest possible robot. The robot consists of 3 links. So as I showed you with link length L1, L2, and L3, there is also a fixed link. And then there are 3 joints, which are marked at O1, O2, and O3. Okay, the whole motion of all the links and joints are in a plane. The joints are rotating about an axis which is perpendicular to this screen, but the links are all moving in this plane. We can also have a 6 degree of freedom spatial robot, and one of the very well-known ones, which we also discussed last week, is the PUMA 6 degree of freedom PUMA industrial robot. So it has 6 joints, and the end effector, which is shown here, can move in 3D space. Okay, so all these wires show how maybe some sensors are attached to the PUMA robot, or it is taking some information from the sensors, or it is powering some motors or some other actuators. One of the sort of very well-known classical 6 degree of freedom robot is this 6 degree of freedom T3 robot. Okay, this was made by a very well-known American company called Cincinnati Millicron. Okay, many of you may have heard of it, but nevertheless. So it is a robot with 6 degrees of freedom. So this is the arm sweep as shown by this red arrow here. There is a shoulder swivel, there is an elbow rotation, and then there are these 3 rotations of roll, pitch, and yaw. Okay, so they are about 3 perpendicular axes. One of the few industrial robots where the wrist has 3 rotations about 3 perpendicular axes. We can also have a 4 degree of freedom SCARA robot. This we had discussed last week. So this is a robot with one rotation about Z1, one rotation about Z2. These two are parallel. Then the last link can move up and down and the end effector can rotate. So if you recall, I had mentioned that this robot was invented for PCB assembling. Basically, you can take a chip, okay, with pins and then take it to the place where it needs to be inserted into a PCB. An important concept in kinematics is something called the degrees of freedom. Okay, so the degree of freedom of a mechanism or a robot is given by this Grubler-Kurzbach criteria. So in this formula, DOF stands for the degrees of freedom. And the right hand side, what you can see is there is something called N, which is the total number of links including the fixed base, okay, or the fixed link. J, which is total number of joints connecting only two links. So if there is a joint which connects more than two links, it must be counted as two or more joints. There is also one term which is sigma I equals 1 through j fi. So this is fi is nothing but the degree of freedom at the ith joint. Okay, so recall last week we looked at if there are two rigid bodies in space, they have 6 plus 6 degrees of freedom. However, when you connect these two rigid bodies with a joint, the number of degrees of freedom reduces. So I had shown you that a rotary joint introduces 5 constraints, or it allows 1 relative degree of freedom. So if this joint were a rotary joint, Fi would be 1. In this formula also there is something called as lambda, which is if lambda is equal to 6, then it is a spatial motion. Okay, whereas if lambda is 3, then it is for planar manipulators and mechanism. So in the case of the PUMA, the number of joints including the fixed joint is 7. Okay, so number of links including the fixed link is 7. The number of joints is 6. And each of the joints are rotary joints, so F1, F2 are all equal to 1, and then lambda is equal to 6 because it is moving in 3D space. So if you substitute all these things here, you will get degree of freedom is equal to 6. The Grubler criteria works very often in many mechanisms and robots. However, it does not work for something which are called over-constrained mechanism. Okay, there's a lot of research going on over-constrained mechanisms has been done. So basically in an over-constrained mechanism, there is certain geometry which tells you that the degree of freedom according to Grubler's criteria is less than 1, but it will move. So recall in this equation, in this Grubler's Kurzbach criteria, there is no mention of geometry or the length of the links and so on. However, in over-constrained mechanism, you have some special dimensions, okay, special arrangement of links which makes it move. Let's continue a little bit. What does the degree of freedom DOF that you calculate using Grubler's Kurzbach criteria indicate? At the basic level, it tells you what are the number of independent actuators that you can have. Okay, so if the degree of freedom of a mechanism is 2, I cannot put 3 independent actuators. The degree of freedom also indicates the capability of the robot or the mechanism with respect to lambda. Okay, so if degree of freedom is equal to lambda, the end effector can be positioned and oriented arbitrarily in that space. If degree of freedom is less than lambda, then lambda minus degree of freedom relationships containing position and orientation variables. Okay, so for example, if you have a motion in plane, and so lambda is 3, but if the degree of freedom is 1, let's say, then I cannot achieve all x, y, and phi. So we'll see later when we look at parallel mechanisms, for example, in the 4-bar, we cannot achieve the coupler or some point on this mechanism cannot give any x, y, and phi. There is some relationship between x, y, and phi. Okay, how many relationships? three of them, because degree of freedom is 1 and lambda is 3. Sorry, two of them, two relationships. Okay. If the degree of freedom is greater than lambda, okay, then the position and orientation of the end effector can be obtained in infinitely many ways. This is a special class of robots and manipulators which are called redundant manipulators, and we'll look at them in more detail later on. In a serial robot or a serial manipulator with fixed base, a free end effector and two links connected by a joint, only two links connected by a joint, you can easily see that n must be equal to j plus 1, and the degree of freedom is nothing but the sum of the degrees of freedom at the joints. If all joints are actuated and are 1 degree of freedom joints, so j will be equal to degree of freedom. Okay, so for example, in the planar 3 degree of freedom, there were 3 joints, okay, and the degree of freedom was 3. In the PUMA case, there were 6 joints, and so j was 6 and the degree of freedom was 6. If j is greater than degree of freedom, j minus degrees of freedom are passive. This happens in parallel robots and closed loop mechanisms. Okay, so for example, if you recall, we looked at something called as a 4-bar mechanism. The degree of freedom of a 4-bar mechanism was 1, but the number of joints were 4. Okay, so some 3 joints are not actuated, they are passive. If j is less than degree of freedom, one or more of the actuated joints are multi-degree of freedom joints. Okay, so you can think of the ball and socket joint or the shoulder joint in your arm. Okay, so between your body and the upper arm, there is a shoulder joint. Okay, j is 1. However, the end of the upper arm can be positioned in 3D space. So this case happens quite often in biological joints which are actuated by muscles. Okay, so I can implement a 3 degree of freedom shoulder joint with muscles, but not so easy to implement using purely mechanical components. A few more definition. If j is the joint variables, okay, and they are typically in a serial robot thetas, which are the link rotations, and d, which are the translation of the links. So all these thetas and d's form the joint space. The position and orientation variables form the task space. So for planar motion, lambda is 3 and the task space is x, y and phi. For spatial motions, lambda is 6 and the task space is the 3 position variables x, y, z and the 3 parameters in a rotation matrix. Often in robots, we have something called as an actuator space. So this is basically due to mechanical linkages, gears between the actuators and the joint variables. Okay, so the joint variable theta is not identical to the actuator variables. Actuator here means the motor. Okay, so the motor could be rotating much faster than the joint, and there is a gearbox. So the dimension of the actuator space, if it is more than lambda, then the manipulator is redundant. Quite obvious. Okay, so if you have if you are moving in a plane, lambda is 3, but I have more number of actuators, let's say 4 of them, so then the manipulator is redundant. If the dimension of the actuator space is less than DOF, the manipulator is underactuated. Okay, so if I have a planar 3 degree of freedom 3R robot, but I put purposely 2 actuators, okay, then it is underactuated. So what is manipulator or robot kinematics? What exactly do we study? We look at the functional relationships between joint space and task space variables. Okay, so we want to look at what is the relationship between thetas or d's and the task space variable x, y, z, etc. So as I mentioned, there are 2 main problems in kinematics of serial robots. First is the direct kinematics problem. The direct kinematics problem is given the constant dh parameters, and the joint variables, find 0 and t. So recall that 0 and t, it means this is the 4x4 homogeneous transformation matrix which contains information about the orientation and position of the nth link with respect to the 0th link. So top 3x3 matrix in the T0 and T is the rotation of the nth link with respect to 0th link, and the last column is the position of the last link with respect to the 0th link. This is the most basic problem in serial robots, okay, or serial manipulator kinematics. So given all the DH parameters, the constant as well as the joint variables, find the position and orientation of the last link or any other link for that matter. This problem needs to be solved for computer visualization of motion and in offline programming systems. Okay, so if I were to rotate or change this DH link parameters and the joint variables, okay, how does the end of the robot move? If I want to show you how on a computer screen, I need to solve this direct kinematics problem. It is also used in advanced control schemes, which we will see later. The inverse kinematics problem, on the other hand, is, as the name implies, we are given only the constant DH parameters and the 4x4 homogeneous transformation matrix of the nth link with respect to the 0th link. We have to find the joint variables. Okay. So this is much harder than the direct kinematics problem. I will show you that. But it leads to a notion of the workspace of a robot. This is a very important concept of workspace. So basically, as the name implies, we need to find the region in 3D space where the robot can operate. Okay, that is in some sense, intuitively speaking, what the word workspace means. And the inverse kinematics problem we'll show leads to this notion of this workspace. This problem also needs to be solved for computer visualization of motion and for use in advanced control schemes. Okay, so let's continue in the rest of the lecture. We will look at direct kinematics of serial robots. So as the problem statement was already given, all the DH parameters are known. So alpha I minus 1, AI minus 1, DI, and theta I, even the joint variable theta I is known. Okay, so if all the DH parameters are known, all the 4x4 link transformation matrices are known. Okay, so remember, the link transformation matrix I with respect to I minus 1 contains all the 4 DH parameters. So taking each row of the DH table, I substitute into the general formula and I can find each of this link transformation matrix. With respect to fixed base zero coordinate system, the position and orientation of link n is nothing but the product of these link transformation matrix. So 0 and t is nothing but 0, 1, 1, 2, and minus 1 t. Okay. So is the problem, direct kinematics problem, more or less solved? Yes, because all the DH parameters are known, all the right hand side is known, so we just multiply matrices one after another and we can find the position and orientation of the nth link with respect to the 0th link. Okay. If you want to find the position and orientation of the last link with respect to some other coordinate system, so for example the base, okay, so then we need to know a transformation matrix between the base to n, and then that is nothing but a product of two transformation matrix. So we want to find base to 0 and 0 to n. So this is sometimes a useful problem because suppose I mount the robot on a moving platform. Okay, so the origin or the fixed coordinate system for the robot is somewhere on the platform, but the platform itself is moving. So if you tell me where the platform is with respect to, let's say, the corner of the room, So that is base to 0, we can find out, and then we can pre-multiply with 0 to nt. Okay. There is also an important thing called the base to tool. Okay, so remember the tool coordinate system is coming after the nth joint. Okay, the origin in our DH convention is on the joint axis. So, and the link is after the joint. And in a robot, that last link, the end effector, can be changed. Okay, so we can have different end effectors for the same robot. So we need a transformation matrix called n tool. Okay, so the tool tip with respect to the nth coordinate system. And if I want to find out where is the end of the tool with respect to the, say, the corner of the room, then we multiply, we need to know what is base tool, this transformation matrix. Okay, and all we need to do is we pre-multiply by base 0, 0n, and n tool. Okay. Let's continue. The direct kinematics problem can be always solved for any serial robot. Okay, why? Because it just involves multiplication of matrices. So there is no reason why we cannot multiply 4 by 4 homogeneous transformation matrices. Okay, this matrix multiplication is completely well defined. So the solution procedure is very simple. It involves only multiplication of matrices. Okay, one advantage of the DH convention that we have used is that the manipulator transformation matrix 0 and t can be computed only once and need not be changed if the location of the base or the geometry of the end effector and tool changes. Okay, this is a very useful reason or very big advantage of the DH convention that we have used. Okay, the other DH conventions, okay, where the origin is not on the joint axis and the link is not after the joint, will have some problems. Okay, there are advantages of those other conventions, but this is the main advantage. So I don't need to worry about what is the transformation matrix between tool and n. I could use different tools. Okay, and a robot is actually supposed to use a variety of end effectors. So all we need to do is this transformation matrix 0 and t I can pre-program. And then whether I mount this robot on a mobile platform or hang it from the roof, which basically means that this base is changing, or whether I choose a small tool or a big tool or a different tool altogether, only this last portion is changing. The main manipulator transformation matrix 0 and t need not change. Okay, a few quick examples. So the direct kinematics problem for a planar 3 degree of freedom robot. Okay, so what did we have? We have 3 joints, okay, at O1, O2, and O3. And in the last lecture, I showed you what is this transformation matrix between the tool coordinate system, which is kept on this schematic parallel geographer, middle of the parallel geographer. Recall, this tool coordinate system is parallel to the third coordinate system, but translated by a distance L3. So 0 tool, this transformation, there is a 3 by 3 rotation matrix, and the last column is the position of this point at the middle of this parallel geographer. And the position was given by L1 C1, L2 C12, L3 C13, that is the x coordinate. C1 here means cosine theta 1, C1, 2, 3 here means cosine theta 1 plus 2 plus 3, and so on. So from the above, you can easily see that the x and y are nothing but this first 1, 4 element and the 2, 4 element, and phi, the orientation of the last link, is nothing but theta 1 plus theta 2 plus theta 3. So the orientation matrix here, 3 by 3 rotation matrix, gives you phi. Okay, and phi is the orientation of the tool. So if I give you theta 1, theta 2, theta 3, and the DH parameters, which are L1, L2, L3 in this case, I can easily find the end effector position and orientation. The direct kinematics problem for a SCARA robot can also be solved. As I showed you, the SCARA robot consists of 4 joints along Z1, Z2, Z3 and a final translation and a rotation. So from the last lecture, 0,4t was again given by cosine theta 1 plus 2 plus 4, and the position of this end effector point XYZ was A1 C1 plus A2 C12 and a minus D3 for the Z coordinate. Okay, so in this case the position of the end effector has X, Y and Z, and if the orientation is denoted by phi of the end effector, we can easily see that the X, Y and Z are given by A1 C1 A2 C12, Y is given by A1 S1 A2 S12 and Z is minus D3. Okay, and phi is theta 1 plus theta 2 plus theta 4. In the case of the PUMA, it is a 6 degree of freedom robot, spatial robot, and as I have mentioned earlier, there is one joint which is vertical about Z1, one joint which is perpendicular to Z1, then another joint which is parallel to Z2, and then there are these 3 joints which are intersecting at the wrist point. Okay. We had again derived the transformation matrix 06T, which is nothing but the product of 2 transformation matrices 03T and 36T that shown last week. And then if you expand all these things and say that the rotation matrix is R11, R21, R31 all the way to R33, you can see that it's a function of theta 1, theta 2, theta 3, theta 4 and theta 5 and theta 6. So the rotation matrix contains cosine theta 1, cosine theta 4, sine theta 5, sine theta 6, all kinds of sine and cosine of all the 6 angles. Okay. The position vector of the wrist point, which is this point here, O6X, O6Y, O6Z, turns out to be a function of only theta 1, theta 2 and theta 3. Okay, and we can show that it is related to the link lengths A2, A3, link offset D4 and the angles theta 1, theta 2 and theta 3 alone. Okay, this is an important observation in the case of the PUMA robot. So in summary, the direct kinematics problem is stated as following. Given the DH parameters, find the position and orientation of the end effector. Okay, and I have shown you with 3 examples how we can obtain this. The direct kinematics problem can always be solved for any number of links. Okay, why? Because it is nothing but simple matrix multiplication. So if I give you 10 links, I need to find 10 transformation matrices, link transformation matrices, and I just multiply these matrices. The direct kinematics in a serial manipulator is unique. If I give you the DH parameters, then we can find the transformation matrix, and the final position and orientation of the last link with respect to the 0th link is unique. It's not possible to find more than one solutions. Okay. And it turns out that the direct kinematics problem for serial manipulator is the simplest problem. Okay, in the next lecture, we'll look at inverse kinematics of serial robots.